Okay, so that quiz, you needed to know the product rule and quotient rule, right? By memory. You also needed to know the derivative of square root of x, which I wanted you to also have memorized. So hopefully you're at that point where you've got those memorized. And now we're going to move on to chain rule, which is what we started last class. And there's like, I've seen probably 5 different ways you can present chain rule to people. I began doing it last class. I was using, the rag and all that stuff, right? I'll give you a couple of other ways of doing it today, but I want to start out with a couple of very important examples, all right? So let's take a look at some examples here. Let's say y equals sine x. All right, I want us to put here what y prime is. This is not a trick question. All right, so what is the derivative of sine x?
Cosine x.
Cosine x. Now, what I want you to now think about is that whole idea that we had, we were covering up, we had like composition, a function inside of a function. Okay, if I was going to try and force myself to see this as a function inside of a function, what would the outer function be here? The sine function. And what would the inner function be? X. X by itself is a function, right? Y equals x. That's a function. So if I were following the chain rule, I would start by taking the derivative of the outside function, right? So I have f, inside of that I have g. So for us we have sine, and inside of that this is x, yes? So what we would do is we would take the derivative of sine first, which is cosine, and inside of that, what would I put? I would put the g function, right? Whatever was in it. So what was in it? X. And then you would put, if you're following the chain rule, times now the derivative of whatever that thing inside was. So what is that thing that's inside? What's the derivative of it? Well, it's x, right? The derivative of that is 1, right? So there's actually a 1 here, and it doesn't change the answer. You just get cosine x. What I'm trying to get you to see is that the chain rule was there the whole time, but because we took the derivative of x inside, we got that 1 here. Understand that? Now let's see how that changes things if I give you another example. And instead of doing sine x, I do sine of 3x. So you have a function inside of a function here, right? The outer function here is sine. The inner function is now 3x, isn't it? So when I apply the chain rule, I first start by taking the derivative of the outside function, which is the derivative of sine, which would give me cosine, wouldn't it? So I'm going to do cosine, but cosine of what? 3x, right? I'm just going to replace whatever was inside there, goes right here, 3x. And then chain rule says times, now take the derivative of what's in here. So what's the derivative of 3x?
3.
Just 3. And so what you get here is 3 cosine of 3x. So do you see how the derivative of sine x, yes, it is cosine x, but if you just tack a 3 next to that x, you actually get a different derivative. It's not just cosine 3x. Understand that? You get 3 times cosine 3x. All right, let's do another one. What if you have y equals sine of negative 10x? What would the derivative of that be? You should pick up on a pattern here at some point.
Negative 10 cosine.
You're going to get negative 10 cosine of 10x. So I already did the part where I had the negative 10 in the back, and I brought it out to the front.
Should be a negative 10x.
Negative, yes, thank you. That's negative in here. Are there any questions on how I got this? Okay. How about this? I've tweaked it a little bit. Okay, so let's start with the chain rule. We're going to be taking the derivative of sine of this rag, right? The derivative of sine of that rag is cosine of that rag. So we get cosine of all that junk in there, negative 10x plus 5. But then we need to multiply, because of the chain rule, the derivative of what's in here. What's the derivative of what's in there? Just negative 10 again, right? Did that 5 really play any role in that chain rule part here? No. Just that negative 10 in front of the x mattered, right? So this is going to be negative 10. And I could write that as negative 10 cosine of negative 10x plus 5. Everybody following along here? All right, so let's see if you can't. Let's see if we like in mathematics to generalize. If we can ever come up with like some sort of generalization or general formula, we like to use them. And the derivative of sine and cosine comes up often enough that maybe it's worth us talking about this. What if you have y equals sine, and inside of it you have ax plus b? In other words, this is a linear expression. So if you have sine and inside of it a linear expression, all of these were linear expressions, right? Negative 10x, negative 10x plus 5. When I had 3x in there, that was a linear expression. So what would happen in general if we have sine of a linear expression? What would the derivative of this be? It would be, okay, so you're ahead of me. I'm gonna write it out and then I'll get a final answer, but we'll get cosine of the linear expression first, right? And then times, and when you take the derivative of this linear expression, the only thing that comes out of it is the a, right? The derivative of b will be 0 because b is a constant. So the a pops out, and so we could take that a into the front. So the derivative of sine of a linear expression is going to be equal to the coefficient of the x term, right? A times cosine of the linear expression. So that a is the coefficient of the x term. That will always happen if you take the derivative of sine of a linear expression. Now, if this is a quadratic expression, that's different. We'd have to actually think about it and see what happens, right? Okay, so let's see if we can't extend this idea to the other 6 trig functions. So let me give you another example. Let's start out with something basic. What about cosine of pi x? Okay, is that a linear expression in there? Pi x, pi is a number, right? So that's a constant. Let's talk about the derivative of this. All right, so we have cosine of something, right? The derivative of cosine of something is what? Negative sine of that something. So I'm going to put negative sine of pi x, and I'm not done, right? I need to tack on to this what? Times pi. Because the derivative of pi times x is just pi. And now this pi can come out front. We get negative pi sine pi x. Are y'all ready to try and do this? You think you can do this now? Okay, let's see. What would you have if you have cosine of a linear expression like this, and you want to take its derivative? So you're going to get that negative, right? Because the derivative of cosine is negative sine. So you know you're going to get a negative. What else is going to pop out? The a again. Because when you wind up doing chain rule, you're going to have to take derivative of what's in here. You're going to get that a to pop out again. So you're going to have negative a sine of ax plus b. So these two, this right here, and then this one right here, are kind of generalizations of what we're doing. And you could do this for all 6. So let's go through the remaining 4, and we'll just go quickly. I'll generalize them right away. I won't give you specific examples. Let's see if you can remember the derivatives of these things. All right, so we do sine, cosine. Let's go to tangent next. So first we need to know what the derivative of tangent is. What is the derivative of tangent? Secant squared. So if y is equal to tangent of some linear expression, then the derivative of this should be secant squared of that linear expression, right? Times a. So that a is going to pop out. Secant squared of what? The linear expression, ax plus b. I'll give you a specific example of, well, I think that's good. Y'all comfortable with that? Okay, let's move on to the next one. We'll do secant next. Secant of ax plus b. So you first need to know what the derivative of secant is. And the derivative of secant is secant tangent. Now, I'll remind you here. The derivative of secant x is secant x tangent x, right? This one students have trouble with. The derivative of secant of something is equal to secant of that something times tangent of that something, right? So when I take the derivative of this, I'm going to get secant of what? Ax plus b times tangent of ax plus b, and then now the chain rule, tack on to the end of this what? A. Now I'm going to put it out front. The thing I see students doing correctly here is they'll do like secant x, tangent x here instead of doing the ax plus b, ax plus b. And if you need, I can do the little cloth here. Derivative of secant of a cloth is secant of the cloth, tangent of the cloth, right? Then times the derivative of what's inside, and that's a. All right, now let's move on to the next one. It was cosecant of ax plus b. So you have to remember what or look up the derivative of cosecant, and it's negative cosecant x tangent x. All right, so that's something I provided to you a while back. Is a negative cosecant x cotangent x. If you look at the derivative of secant and cosecant next to one another, I think there are some similarities here. Do these kind of look similar? Like, if you can remember secant x tangent x is the derivative of secant x, then the derivative of cosecant x, isn't this just the reciprocal? Or not reciprocal, but the opposite. Instead of secant, which is 1 over cosine, it's 1 over sine. Instead of tangent, it's cotangent. It's like the opposite ones. But then you have to remember the negative, all right?
It's like sine and cosine.
Yeah. Okay? So, what's the derivative of this? So we're going to get negative a. That negative a is popping out of that chain rule at the very end, but I'm moving it out to the front. And then what? Cosecant ax plus b, cotangent ax plus b. And just to be thorough, let's finish it off. The last one, y equals, what's the last one? Cotangent x? Or cotangent of ax plus b? Now the derivative of cotangent x is negative cosecant squared x. So this is going to be, again, a negative a pops out because of chain rule, and then it's cosecant squared of ax plus b. They have these new markers down in the office that are refillable. They look pretty good. They write pretty good. I'm impressed so far. All right, questions? Now keep in mind, this is only the derivative of the 6 trig functions if you're plugging in linear expressions, right? If these are something other than linear expressions, this formula won't work. The reason why I'm showing this to you is because this actually comes up a lot. A lot of times you have linear expressions inside of trig functions. And especially in calculus 2, a lot of times we're trying to work with things that look like this. And so it's kind of good for us to see kind of a generalization of those now. Let's take a look at something that's not like this, that requires a little more effort, all right? All right, so let's try something here. If you look at it, if I can give you an analogy, which I've always been known to give terrible analogies, all right? So like when we had the first rule for derivatives was the power rule, right? And that was like we just like barely opened the window a little bit in terms of what we could actually do, all right? We just kind of cracked the window. We could just do derivatives of power functions. And then we started adding more rules. And like if we can take the sum and difference and take derivatives. Then we got the product rule, so we're starting to open up that window a lot more as far as what we're able to take and do. Quotient rule, even more, right? But the chain rule is like blowing the whole entire wall down. I mean, it is now with chain rule, we can do basically the derivative of just about everything. The things we can't do derivatives of right now are only functions that we haven't discussed their derivatives yet, like exponential functions and logarithmic functions. We will do that, just not yet. But the chain rule really just kind of like, once you have chain rule, exponential and log, you pretty much can do like 95% of all derivatives that could be possible, if that makes sense. There's nothing that someone can hand to you that you can't handle. There's no other rules, understand? Okay, so let's do this one. How about sine? So far everything looks good. Y is sine. And then x, that looks like a linear expression so far, looking good, times cosine x. Okay, I just screwed it all up. That's no longer a linear expression inside, is it? Now I put x dot cosine x, right? Normally that dot won't be there. Okay, so that dot was almost a little hint to you. So what you have in this problem is a combination of 2 different rules. You have a product, don't you? But that product lives within another function. So you have a chain rule happening here, and inside the chain rule you have a product rule. So let's discuss the order in which we do things here. What would the outer layer of this be, the outer function? Sine, right? So if I'm going to follow this chain rule, then what I need to do to take the derivative is I need to, again, cover up the inside. Are y'all okay with me doing it like this? Okay? Like I said, there's like 5 different ways you can do this, and there's like tables we can make and all this stuff. But at the end of the day, when you walk out of here and you're done with Cal 1, you should not be making tables and charts to try and take derivatives. It should all be done almost like a mental process. All right? So I'm showing that to you right now because I want you to get there as quickly as possible. We're taking derivative of sine of this cloth, which is cosine of that cloth, which is x cosine x, right? Okay, times. Now, the next part is the derivative of what's in here, right? So because I want to kind of keep track of things, watch how I write this. I'm going to write x times cosine x, and then I'm going to write derivative. I haven't taken the derivative. This is just to let me know that I've done the first part of the chain rule, okay? The derivative of the outer function evaluated at the inner function, times now I need to take derivative of the inner function. And I'm going to go ahead and come over here, and I'm going to do some scratch work. SW stands for scratch work. And I'm going to take the derivative of x times cosine x. And to do that, I need to use the product rule, right? Okay, so the product rule on this, I'm going to take the derivative of this times this plus the derivative of this times this. which is what your homework was over last time, right? So derivative of this is 1. I'm going to write it. You don't need to. Times cosine x plus, now derivative of cosine x, negative sine x. I put it in parentheses because the plus negative is weird. And then what am I missing here? Times x. That finishes off the product rule. Derivative of the x times cosine x plus derivative of cosine x times the x. And now clean it up. This is just cosine x minus x sine x. That is this, right? So I'm just going to get my answer here. I believe I'm at the end. You'll have to tell me whether or not I am or not. Cosine x minus x sine x. Is that correct, like that?
Put it in the front.
Well, put it in the front. Yes, I could. But is it correct written the way it is right there? Yes? Do I need parentheses around this? I do, because there's more than one term, right? And so when you're saying it's all of this junk times this, if there are two pieces, then this technically would have to distribute to both of them, right? If you don't write the parentheses, all you're saying is these two multiply. This one never gets touched. So you have to have this in parentheses. That makes sense? Now, when this was a nice number, right? When this was like, or something like 3x or something, we moved it out to the front, didn't we? But when it's something big and ugly like this, just you can leave it there. I mean, it's not incorrect to leave it like this. Just keep in mind what's happening here. You are taking cosine of this, right? Whatever that is, times this stuff. Right? So in other words, the cosine is only operating on this piece. This cosine has no impact on this piece. Right? Okay. That's it. So there we saw a chain rule that within it there was a product rule. As you can imagine, this can get pretty messy, right? Like you can have all sorts of different variations of anything you can think of, really. All right, let's try something else. I want to stay within, I had some problems out of the book that I wanted to do, so let me try and keep myself on track, because I'll go crazy. I'll put some stuff up here. It's all madness. Okay, how about this one? How about x to the 4th plus x to the 7th times 3x to the 6th plus 1. No, let's not make it 1. Let's make it 10 x cubed, and then all of that to the 10th. That is a function, right? That's actually a polynomial function. If you had enough time, maybe over spring break, you could take this and you could raise it to the 7th and multiply it out, right? Then you could take this and multiply it out, 10 of them, then collect all your like terms, and you would have this huge long polynomial, right? And then what we want to know is, the slope of the tangent line at different points on this polynomial. But doing that would be a disaster, right? Trying to expand this. These rules should help us get the derivative without having to do all that expansion. What do you see happening here? You see a product rule? Everybody see a product right here? Okay, so let's start trying to think critically. If I have a product right here, the product rule says that I have to take the derivative of this times this plus the derivative of this times this, right? Now, when that means I'm going to have to take derivative of both of those at some point in time, right? When I look at this one by itself, that's a chain rule to take the derivative of that, because it is a function with an outer function of being raised to the 7th power. So it's like a function within a function. And this one is also a function within a function. Do you see how quickly this is becoming complicated? That's why I gave you a quiz today. We can't do today if you can't do product rule. We can't do today if you can't do quotient rule. And as we move forward, you can't do anything else without chain rules. So these are all necessary conditions for progressing through the course. You know, sometimes in math courses you can get through like certain sections and you can like not get it and you can still survive. You can't survive without product, quotient, and chain. You just can't survive calculus. All right, you ready? Okay, so I'm going to do this one again in steps to kind of help us. The derivative of this should be the derivative of the first one, right? Okay, so watch how I write this. This is just because this is our first time seeing something like this. I'm going to take, I don't want to use a different color because y'all don't have different colors. I want to take x to the 4th plus x to the 7th, right? I want to take that, I want to take its derivative, right? And then I want to multiply that times what? This one, right? Without a derivative. Why am I not taking the derivative on this one? Because that's what the product rule says, right? Okay. And then what? Plus, right? Plus, now the derivative of this one, right? So I'm going to put it in brackets. The reason I'm not actually taking the derivative right now of this piece is because it's actually a little too complicated for me to take the derivative of right now. So I'm just kind of getting everything laid out first. What am I missing? Am I done? What?
No.
What do I need? I need to multiply that times x to the 4th plus x, all of that to the 7th. So back good old, this is your f prime g plus g prime f. That's what we've got there, right? All right. So I'm going to do now 2 separate scratch work problems. I'm going to do this one on the side. After I get that, I'm going to do this one on the side. Understand? And then I'll come back to this and I'll plug everything in. It's going to look horrible, but it's still better than me having to expand this out, right? And expand that out. And if you say, well, I'd rather do that, then I'd change that to 100 and change that to 700, and then eventually I'd make you submit, right? This will work, though. This method will work. So here we go, scratch work. I'm out of space. If I were you, I'd move to the side somewhere and do this. I need to take the derivative of x to the 4th plus x to the 7th power, right? I need to take the derivative of that. And I said this is chain rule. Now, do you all understand why that's chain rule? You have a Elmo, that's the name of that little device. So this isn't an Elmo remote control. We have an Elmo remote control raised to the 7th power. And therefore, the derivative of that should be what? 7, right? Because that's what we do with powers. We bring the powers out, we subtract 1. So the derivative of this should be 7. And then in parentheses, the Elmo, right, which is x to the 4th plus x, but raised to what power? 6. Are we done? No, because now we say, chain rule says multiply that by the derivative of what was in here. And the derivative of that Elmo is what? Something I can handle, right? 4x cubed plus 1 in parentheses, because it's multiple terms. So you have to have that in parentheses. Is this good? That piece right there, remember this right here, that there is just that, right? That's all that is. I still need to do this one. Now again, because I'm out of room, I'm going to go ahead and slap that on right now. This right here is this 7 x to the 4th plus x to the 6th, and then times in parentheses 4x cubed plus 1. That's just that, right? I'll come back and I'll bring everything else down here in a second. All right, my secondary scratch work is to do the derivative of this one right here. So let's see, I'm going to take 3x to the 6th plus, man, I really like these markers. 10th derivative. You may not like this set of parentheses I put here, but if I take these parentheses out, that's just kind of weird notation. To have this with 10 to the prime, it's more common in a book. You're going to see there's a set of parentheses here or brackets to let you know, hey, look, we're taking derivative of everything in here. All right, same thing. I don't think the Elmo will fit there this time. So I might have to use, let's use this water bottle. Let's just use everything in the classroom today. Okay, so we have this spray bottle to the 10th power, right? So the derivative of this should be 10, the power comes down, spray bottle, which is this, all to the 9th power. So that's just your power rule on that chunk right there. And then I need to tack onto this with multiplication the derivative of the water bottle, which was what? What is it? 18 x to the 5th plus 30 x squared with parentheses. That's the derivative of the inside. Okay, I'm ready to write this derivative out. Here we go. I'm going to save that right there because I'm going to need it. All right, so I had the derivative of this. We already got it. Times 3x to the 6th plus 10x cubed to the 10th. That just came right down. Never even did anything with that. Plus, now the derivative of this, which I just had right here. So plus 10, 3x to the 6th plus 10x cubed to the 9th times this chunk right here, which is 18x to the 5th plus 30x squared. Wonderful. So that piece is just derivative of this. Still have this, though. So this piece has to come. X to the 4th plus x to the 7th power. This gives you the slope of the tangent line to that curve at any value of x. All right? Now this, again, is what I call the raw derivative, but we actually could clean this one up. I know it doesn't look like you could clean this up, but I want you to notice something here. You have some common factors. Look, you've got an x to the 4th plus x, right? And you've got 6 of them. And then here's our addition, right? So this is a separate term over here. We have an x to the 4th plus x to the 7th here. So this one has 7 factors of that, and this one has 6 factors of that. So can't I pull out 6 factors? Watch the way I write this. I'm going to pull out x to the 4th plus x. I said I'm going to pull out how many factors? 6. Okay. What else do we have in common in both of these terms? In this and this, what do we have in common? This one right here, 3x to the 6th plus 10x cubed. I have 10 factors of that. And then here I have the same thing and 9 factors. So can't I pull out 9 factors? Okay, so if I pull out 9 factors of that, I'm going to get 3x to the 6th plus 10x cubed, and I'm pulling out 9 factors. Anything else that they both have in common? Like these two don't match, right? These two are not the same, so I can't do anything with that. How about constants? I have a 7 here, and I have a 10 here. I can't pull out a common factor in terms of a number. So that's it, right? That's all I can do? So that all got pulled out. That means I have either a parenthesis or a big bracket, and now I need to write out what's still in here. So if I pull these 6 factors out, and I pull 9 of these factors out, then what I'm left with is the 7. That got pulled out, right? Yes. This and 1 factor of that. So I have 7, 4x cubed plus 1, and then 1 factor of 3x to the 6th plus 10x to the 3rd. Make sure you understand that step. If I multiply this in here like this, it will kick out this thing, right? It will bring me back to this piece. Then I need a plus sign. I need the 10. How about these factors? I pulled out all of them, right? So all of these are gone. I did not pull this out. So I still have 18x to the 5th plus 30x squared. And how about this? I pulled out 6 of them, so I still have one of those there. X to the 4th plus x, all of that closed off. Okay, so I have actually factored that, haven't I? Now, as bad as this looks inside, could we do this math? Like when we were here, back on this line, I don't think anyone here wanted to expand that 6 times or expand that 10 times, right? But look at this. Could you put these two together? You just do a FOIL, wouldn't you? Because both of these are not raised to any powers, so you could just FOIL that out, couldn't you? And then over here, could you just FOIL those out? And if you did that, you'd probably be able to collect some like terms together, right? Okay, let's do it. Algebra on steroids. All right, so here's where I am. This is equal to x to the 4th plus x all raised to the 6th, and then I pulled out 3x to the 6th plus 10x cubed, but that's all to the 9th. Then I had my bracket, and I'm going to put my answer up here, but I'm going to try to do some of my work right here. If I distribute, and I'm going to wait on the 7, okay? I'm just going to distribute. I'm doing this, 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 this. So help me out. What would I get here? First term would be 12x to the 9th, and the next one would be 40x to the 6th. So that's this times this. And then the middle or inner one would be plus 3x to the 6th. And last one, 10x cubed, right? You okay with that? Let's collect anything we have together here. 12x to the 9th plus 43x to the 6th plus 10x cubed. So that's what these two together would be, right? But what do I have in front of it? 7. A 7. So I had a 7 in front of that, and I had a 7 in front of that. Let's distribute the 7 through. Someone get a calculator out. And whatever we get, we're going to slap it right here, okay? So what's that, 84 x to the 9th? And then what? 301 plus 301 x to the 6th, and then plus 70 x cubed. All right, this right here is just that piece, right? I still have to do this. I have to expand this one. Same thing. I have a 10 out front. I'm going to do this, 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 right? So let's try and do this mentally, okay? I don't know if we can do this. This times this would give me what? 18x to the 5th times this would give me 18x to the 9th. I'm going to eventually hit that with a 10, which is going to be 180x to the 9th. Okay, I'm going to put that here. 180x to the 9th. Okay, the next multiplication is 18x to the 5th times x, which is 18x to the 6th, but I'm going to hit that with a 10. So 180 x to the 6th. Now I do this middle one. 30x squared times x to the 4th is 30x to the 6th. Hit that with a 10. 300? x to the 6th. And finally, 30x squared times x, 30x cubed, but hit that with a 10, so 300x cubed. I'll put these two together, that's 480x to the 6th. So I'll have this, plus 180 x to the 9th, plus 480 x to the 6th, plus 300 x cubed, and I can now close the bracket. And we would be one line away from the end, because this in here has like terms in it, right? You could put these two together, those two together, and those two together. Yeah? What do y'all think? Come on. I need an honest reaction here. It's stupid? There you go.
We're gonna get that.
I like that.
In how to.
No, this one is pretty ugly. Yeah. This one got pretty ugly. Yes.
Question: how would you use this in the real world?
That's a great. I mean, you always have to ask that question, right?
Yeah, I mean,
All right. Well, I have a couple of answers for you. All right. As far as needing to take derivatives in the real world, I mean, a lot of technology relies on the calculus to find the instantaneous rate of change of something. Okay. Now, for what? I mean, you think just about anything that involves math or science is going to have calculus and derivatives in it. Okay. Differential equations are also used. They use derivatives in there. I mean, so pretty much any advanced like physics, if you want to drive your car, there's calculus in there, right? Now you're asking, where would you use this? It's used every day, but it's not something you would need every day, right? Like you would never need to do this, ever, okay? You're never going to sit down and have to take this derivative in the real world, right? It's not going to happen. It's not, unless you're teaching people how to do it, right? Okay, so that actually brings a more profound question into play here, and that is, why are we doing this, right? Why are we doing this? And so my answer to that, because I've toiled with this for years, the same, having an answer to the same question you have, is that it's about whether or not your brain is capable of doing this type of thing. There's a lot of things going on here, right? There's a lot going on. And as you progress through calculus, and whatever your major is, your brain is having to think a certain way about things, right? You're thinking critically about things. It's different than if you're like a history major, right? That's a different part of your brain that's required for that sort of thing, right? But everyone here is a STEM major, right? So the idea is that if you can complete a STEM degree, like what's your major?
business.
What are you doing?
University of Boston. They want calculus too.
Cal 2 for what business?
For American homeschool business. They require calculus too.
So why do you think they want you to have calculus 2?
To see if you complete something.
Because that's how you can weed out people who are not capable of thinking at a higher level. Okay? I mean, really, that's what it comes down to. That's like when I first started teaching here, what was required to become a doctor was stats or pre-cal. Stats or pre-cal, and you could go become a doctor. Problem with that, too many people wanted to become doctors. So where do you weed them out? You just up the math requirement, right? Now it's up to like Cal 2. For a lot of major universities, you need Cal 2 if you want to go to med school. That's a weed out course. But it's because not a lot of people can think at this sort of very analytical like way. But doctors need to think analytically. They need to be problem solvers. And that's my ultimate answer to you is that, look, you have different types of people, and we're not going to get all philosophical. I have a lot of friends who are engineers, and my brother's an engineer, and I always talk to them every time we have a get together and we're sitting there, and I'm like, if I could tell my students anything about why they need to be doing the calculus and stuff and try and convince them why, it's because you have to become a critical thinker, and you have to become a problem solver. And this is very good exercise at becoming a problem solver. You're faced with something, you have to do all these steps and processes, you can't screw anything up, everything has to be perfect. And some people see something like this and they're just intimidated by it, and they kind of crumble up and, kind of wilt away, and they can't handle the stress of the problem. And these aren't even like word problems yet. These are just like, we're just working with tools right now, right? I was telling my 8-year-old daughter the other day, because we were she likes to solve linear equations in her head. So I give her 5x minus 4 equals 2x plus 1, and she'll sit there and she'll move things around her head. This is her. I'm not pushing this on her at all. And she's asking me Daddy, am I doing really hard math yet? And I'm like, you know what? Math, these are tools, okay? That's all these are. We haven't really started building anything yet, right? We haven't built anything with these tools. We're not actually solving any real world problems yet. But we can't solve those real world problems if we can't do the mechanical. It's like asking you to build a house without properly knowing how to use a nail gun, or not giving you the right lumber. It's just, you got to have the tools in order to, is that a hand? No? Are you waving?
No,
okay. So I don't know if I'm answering your question or not. I mean, you're never going to need to take a derivative, okay? Never. I don't think you ever will. And if you're in the real world, like in an engineering firm or something, you're probably going to have a computer do the derivative for you, because they're not going to trust your answer. They're going to trust the computer over you. I mean, they come into you and they put a problem in front of you, and they know that you can do that problem. That you're not going to where's the solution key? Let me get on YouTube and see if there's a problem just like this, so I can just figure out the answer without having to actually think about it, right? You know what I'm saying? I don't know if that's a good enough answer.
Can I say something?
Yes.
Okay, so I'm in differential equations right now. And recently we got a quiz, and going back to what you said about the computer, there was a problem in there, and some guy checked it on the computer, and in there, do you mind if I write on the board?
You want to?
He wrote
But since you volunteered yourself, Diego has been in my Cal 1 class, Cal 2, and Cal 3, and he's just coming back and he's taking this class again to kind of just, he's a math major, so he just wants to take this again to kind of, first time through, it's a different experience. So he's just kind of auditing the class to get a grade. All right, so he can speak from a little further down the road, so apparently he wants to say something.
So it was what's called an integral, which is the opposite of the derivative. And for the answer, he put this.
Oh.
We don't even know what that means.
Oh yeah, okay.
And he put that, and he's like, that's the answer. But he didn't know what it meant. And it was something that it was a strange problem, but you could still do it by hand. You have to be able to know that. You can't just put that down and say, that's just the way it is. Especially in these classes.
Let me clarify. Mm-hmm. Thank you, Diego. Mm-hmm. Basically, the problem, this was the answer that Wolfram Alpha, the computer, gave him. All right? The computer is saying that this is an error function, which is a function, but that answer makes no sense in terms of there is a real solution you can get to. So even in engineering firms, they rely on computers heavily, but there's this thing that was referred to as the black box. Okay, you have the black box, and this engineer has a problem, and they get to a point where they need to do some math. So they go to a computer, they sit down, they've got this engineering software, they plug in their problem, and then out comes the answer. They have no idea at all how that answer was arrived, right? The computer's just zeros and ones, electrical signals, that's all it is. Somebody wrote a program to solve the problem. So they get this answer and they trust it, they go build a bridge based on that answer, right? Somebody has to know how this black box works. So when I was in graduate school, one of the problems that we had, one of the courses I took, was we had to pick 3 commonly used mathematical programs, and we had to find we had to create a problem that we could prove by hand, mechanically, what the answer was, and then send it through the program and create an incorrect result. So we had to study the code and exploit a weakness within the code so that you could show that you can't always trust this, and you always have to have somebody who understands the mechanical part behind that. That means we're always going to have people who can do this. Because if you remove yourself too far from all of this to just trusting this, then things can get very dangerous later. Now, we don't need everyone in here to be able to do this, right? But we need some still. All right, we've gone way off topic. Good question, but I got to get back on track here. I think once we get to some word problems, you'll start to see the real world connection a little bit better. This is still me saying hold the nail, hammer, straight level, hit, hit, hit. I mean, this is still very much me teaching you the tools. We have not addressed anything really worthwhile, I guess. Okay. How about something that looks really different? How about f of t, use a different variable, is the cube root of t sine t. So do you see what's happening here? Can anybody tell me what we have here? We have a function and a function. Remember on the last problem, it was like a product, and then we broke it down in the product, but certain parts of the product were chain? This one, we do have a product, don't we? Do you see the product? Where's the product? T sine t. So are we going to do this the same way and break it down like we did, or is it not that?
Sir, is it two chains because of the square root, or?
This is a cube root, so that's just a single root,
Oh,
just the cube root. But the cube root is kind of like the outside layer of this, isn't it? And then inside that you have your product. So we actually have a chain rule. And inside the chain rule, we have a product rule. Yeah? Yes?
Question.
Mm-hmm.
Can you rewrite that as t sine t, but it puts t's raised to the 1/3?
That's what I was going to suggest we do. I was going to suggest we rewrite this like that, because that's what it means. And that's why in college algebra, we always want to make sure you understand that we can always convert radical notation over to rational exponents. Do you see why rational exponents are important now? Because in calculus, you use power rule. And power rule means you need to pull this power out. And when it's written as a radical, it's not so clean. It's not so easy to see that. So if we just convert everything over to this, now we see the power coming out. So yes, that would be my first suggestion right there, is to see that. All right, let's try and go for this derivative. F prime of t equals. Now I've got that thing there, this thing right here, to the 1/3 power. So we're going to bring that 1/3 out, right? 1/3, and then we're going to take everything that was in there, t sine t, and we're going to raise it now to what power? Negative 2/3. We're subtracting 1. So 1/3, take away 1, that should give you negative 2/3. Times comes from the chain rule, right? Now the derivative of what's in here, right? And that is a product rule. So let me write that down. I'm going to take now t sine t, and I need to take its derivative. So I'm going to have to go and do this and write it on a, go to the next line, and I need to figure out what this derivative is. So 1/3 t sine t minus 2/3 times, now all of this, whatever my answer is, it's going to be in parentheses, isn't it? And I'm going to be doing the product rule right there. So I'm going to have derivative of this times this plus derivative of this times this. So what's the derivative of t? Just 1, right? It's times sine t plus derivative of sine t, which is cosine t times t. So how about I write it like this? And we're done. We're done. That one wasn't so ugly, I don't think, right? Okay, look at this one. So I'll share something with you because you got me thinking now about, why we do this and all that. So I told you my brother is an engineer, right? And I can't tell you who he works for, but it's a company in Austin and nationally, known company, worldwide actually. And his interview questions, right? When he was given the interview for the job, there were a few, but the two that he told me that I always remember, I like to tell my students, was the first one was if you have 12 identical coins, okay? 12 identical coins. So you look at them, they all look exactly the same, but one of them weighs just a little bit more than the others, but not where you could notice it, right? Okay, so you've got 12 coins, one of them is a little heavier than the others. And you are given a balance. Not a scale, but a balance. What is the minimum number of weighings that you would have to do in order to find that heaviest coin? So how many weighings would it take to isolate that heaviest coin? What's the minimum number to guarantee it? I mean, you could just pick 2, right? And get it, and first try you get lucky, right? That's not what they want. They want to know the minimum number of weighings that it would take to do that. That was one question. And then he had to sit there right there and answer. He didn't have time to sit there and let me come back to you on that, right? So problem solving, critical thinking, right? This is not calculus, this is critical thinking. If you're not trained to handle that sort of pressure, you're not going to be able to answer this question. But let me get on Google, or let me YouTube. Let me see if I can find a YouTube video, right? Or Chegg or something like that, right? So, do y'all have what I heard 4?
It'd just be 1, because you could put half of the coins on one side of it, and then the other half on the other one, and the one that weighs more should have the coin that's right.
That would give you the stack that has more. That doesn't give you the coin though. Right? Okay, so it sounds like y'all want the answer. Okay, so what do you do here? What's the minimum number? Minimum number of weighings, 6. I'm hearing 6, I'm hearing 4. Okay, here's the correct answer. So you start out and you put 6 on each side, right? Okay, so let's just say we put 6 here, 6 here. Let's say this side goes down, right? That side goes down. So you've done one weighing, and you know it's in this stack. There's 6 coins there. So you take that, right, and you do what? Half it. Put them on here again. Let's say this side goes down. So now I've done 2 weighings, right? And I've got 3 coins here. Now, 1, 1, and 1 in my hand. If these are balanced, I've got it in my hand. If this one goes down, that's it. This one goes down, that's it. 3 weighings. That's the answer. That's the correct answer. Okay? All right, so you can see that took some critical thinking, right? You could say 4. Yes, you could do it in 4, but it's not the most efficient way to do it. And that's what they wanted, the most efficient way to do it. So I'm sure someone said 4,